Hey everyone, and welcome. Today we're diving into a really cool story about how a classic, decades-old idea from operating systems completely solved one of the biggest bottlenecks in modern AI. We're going to see how it makes the large language models we use every day, well, dramatically faster and cheaper to run.
So, it all starts with this one central problem that anyone building with AI runs into. You've got these incredibly powerful models, right? But trying to serve them to millions of users is just brutally difficult. Even on the absolute best hardware, the throughput is low and the costs are sky high. So what's the deal? What's the real bottleneck here?
Well, the answer, as it so often does, comes down to memory. To be specific, if you want to unlock high-throughput, cost-effective LLM serving, you've got to figure out how to manage one very, very special kind of memory.
And that special memory is called the KV cache. See, for an LLM to generate a new word, it has to remember the context of all the words that came before it. All that context gets stored in this thing called the KV cache. And as the model writes out its response, that cache just grows and grows. It's totally essential, but as you'll see, it's also a huge source of inefficiency.
I mean, just look at this. Look at how much of this precious GPU memory the KV cache eats up. On a standard 40-gigabyte GPU running a pretty common 13 billion parameter model, sure, the model weights take up the biggest slice, but that KV cache can consume a massive chunk of everything that's left. Wasting even a tiny part of that memory means you can serve fewer users at once, and that drives your costs right through the roof.
And unfortunately, the old way of managing all this memory was, to put it lightly, incredibly wasteful. Before the breakthrough we're about to talk about, serving systems were basically just throwing away most of the KV cache memory they had available.
So the problem really came down to three main culprits, these three types of memory waste that just plagued the old systems. You had internal fragmentation, reservation, and external fragmentation. Let's break down what these actually mean.
Okay, so first up is internal fragmentation. This happens because you have to guess how long the model's response is going to be and reserve a chunk of memory for it ahead of time. It's kind of like booking a hotel room for a full week, but then you check out after just 3 nights. You still paid for the whole week, right? And the hotel couldn't give those empty nights to anyone else. It's just pure waste.
External fragmentation is just as bad, if not worse. Imagine a parking lot where cars of all different sizes have been coming and going all day. You're left with all these small, empty spots scattered around, but none of them are big enough to fit the bus you're trying to park. The total amount of empty space is huge, but because it's all broken up into these tiny, unusable pieces, it's completely wasted.
So, just how bad was this problem? Get this. When researchers profiled these older systems, they found that only 20 to 40% of the KV cache was actually being used. That means a staggering 60 to 80% of this super valuable GPU memory was just gone, wasted, all because of fragmentation.
Okay, but this is where our story takes a brilliant turn. The researchers behind a new system called vLLM, they realized that this problem, it wasn't exactly new. In fact, computer scientists had solved a very, very similar problem decades ago, just in a completely different context. And here it is, the aha moment. They decided to apply the classic idea of virtual memory and paging, the exact same technique your computer's operating system uses to manage its own memory, and apply it to the KV cache on a GPU. This, right here, was the key.
So how does this old trick actually work in this brand new setting? Well, the technique is called PagedAttention, and it's just an incredibly elegant solution to that whole fragmentation nightmare we were talking about.
So instead of allocating one giant, continuous chunk of memory for every single request, PagedAttention first breaks the entire KV cache into small, fixed-sized blocks. Then it uses something called a block table, which is just like a page table in an OS, to keep track of which blocks belong to which request. And here's the crucial part. It only allocates new physical blocks on demand, as a sequence actually needs them. No more pre-allocation, no more waste.
And this is where the magic really happens. From the sequence's point of view, the logical view, its memory looks perfectly neat and continuous. But in the physical reality of the GPU memory, PagedAttention can store those blocks wherever there's a free spot. They don't have to be next to each other. This completely eliminates external fragmentation. It's like being able to park that bus by breaking it into car-sized pieces and just fitting them into any spot you can find.
But it gets even better. This new memory model does more than just save space. By virtualizing the KV cache, it also unlocks some seriously powerful features that used to be super inefficient, like sharing memory between different requests.
This is all possible thanks to another classic OS technique called copy on write. The idea is really simple. If you have multiple requests that are all sharing the same memory blocks, you don't actually make a new copy for each one. You just let them all point to the original blocks. It's only when one of those requests needs to change the data that you finally make a separate copy just for it.
So, what does this actually let you do? Well, imagine asking a coding assistant for, say, 5 different function suggestions from the same prompt. With PagedAttention, the memory for your initial prompt is stored only once, and it's shared across all 5 of those requests. This makes complex things like parallel sampling and beam search incredibly memory efficient, which just boosts throughput even more.
Okay, so the theory is super elegant, but what does this all mean in the real world? Let's talk about the impact. The performance gains are, and I am not exaggerating, absolutely astronomical. The numbers really do speak for themselves. The vLLM serving engine, which is built on PagedAttention, achieves up to 24 times, that's 24x, the throughput of a standard Hugging Face implementation. It's also over 3 times faster than other highly optimized inference servers out there. That is just a massive, massive leap in performance.
And of course, higher throughput translates directly to lower costs. For the very popular Vicuna chatbot demo, switching to vLLM allowed the team to cut the total number of GPUs needed to run the entire service in half. A 50% reduction in hardware costs is a total game changer for any production application.
Now, you might be thinking this is just some niche academic project. Nope. PagedAttention has been so unbelievably effective that the algorithm has actually become the new industry standard. All the major inference frameworks, from Hugging Face, NVIDIA, you name it, they've all integrated it into their core serving engines.
And maybe the best part, especially for all you engineers watching, is how ridiculously simple it is to use. The vLLM library is just a Python package you can pip install. In literally a few lines of code, you can load a model and start serving it. And you get all the incredible benefits of PagedAttention handled for you automatically. It's so powerful and yet so accessible.
You know, when you step back, it's pretty amazing. One of the biggest leaps forward in modern AI serving didn't come from some brand new neural network architecture. It came from the clever application of a 50-year-old computer science idea. It really makes you wonder, right? What other time-tested principles are just sitting there, waiting to be rediscovered to solve the huge AI challenges of tomorrow? Thanks so much for watching.